right? So this is what the angles are that happened to me in this second situation. And now, this is actually an identity, and the thing is correct. Okay. Yeah, and so actually, in general, if you look in the Niels Schwang book, which I advised you to look at for quantum computing basics, it gives you a little theorem for a general 2x2 unitary down here, how you can build a circuit that actually makes it use only C nodes and 1-qubit rotations. So that's a known thing, and this is a special case of that result. Okay, so that was, a little afterthought after yesterday. I hope like this it's all clarified. So for today, my topic, I'm not coming back to QPE, that was yesterday. So today, I'm going to tell you more about this second strategy for doing quantum computing for many-body systems, which is this variational quantum Eigensolver. I gave you a bit of that yesterday, but let me be more extensive today. So a typical circuit, doing this job would be, let's say, as follows. So there's some kind of black box with lots of qubit lines whose task is to produce. So this box is parameterized by a bunch of angles. So let's say theta s or so. And what it does, if we start from everybody trivial, 0, 0, 0, this thing produces a state, which yesterday I think I called psi trial, which is parameterized by all these angles. So we have to talk about what's in the box, but let's leave it for now. So somehow we have this good idea of setting up this trial wave function. And then the rest is very simple. There is, a bunch of measurements of operators. So here it's like a measurement block. And what you measure is the Hamiltonian. Hamiltonian will be expressed as a sum of elementary operators like x or x times y or x times y times z. Those you can measure by going to the right basis and doing a standard measurement. Okay. So here you measure. You measure h, so to say, your Hamiltonian that you're trying to minimize, to find the ground state of. So that gives you outcomes, E of, depending on all these thetas. So that's what one run of the circuit will give you. And then, comes this cycle where you try to improve your thetas, do it again, try to get to a lower energy and keep optimizing until you've hit the bottom and your circuit has optimized performance, and you get as low as you can using this ansatz. Okay, so here's like an optimization cycle. Okay, and let's see. Okay, so when you're done, there is this optimal energy, which is an upper limit. So the E that comes out, E opt, say, is an upper bound to your ground state by general principles. So I'll go into some examples quite soon, but a few general things about, let's say the merits of this and also where the trickery sits. Typically, for example, if you look at quantum chemistry applications of this method, there's a lot of pre-processing before you start doing this procedure. And in particular, you like to, for example, this H here will be a sum of terms. We'll see an example as we go. So you have to measure these terms one by one. You can't measure a sum, you measure a single Pauli word, so to say. So if your H has, let's say, 10 terms, a single measurement is 10 times running the circuits and doing a measurement. And this you have to do lots of times because of this cycle here, right? You keep changing your thetas. So it really pays to go to a basis where your H has as few as possible terms. That's really important. If you do like a naive basis, typically you can improve a lot by doing smart rotations and other tricks. So it pays to do all that before you go into this. So that's rather clear, but still where a lot of gain is possible. And then of course comes the question, what's in the box, right? So it's easy to make, I can put lots of nuts and crazy gates with angles to make some kind of scattered random state. But my hope of hitting the actual ground state, if I do this kind of without reason, is pretty low, right? For example, if I give myself 10 thetas, I can kind of explore 10 dimensions, but my Hilbert space is 2 to the n, right? And I'm trying to hit a needle in a haystack, which is my ground state. So there has to be some, well, a lot of kind of insight or intuition going into your thoughts. And if you don't do that, you're probably going to miss big time the energy, and this will be a bad rather than a good approximation. So that's a bit of an art, right? So getting this thing right is a delicate thing to do. Yeah, and I'll have 2 examples today, maybe just to announce what will be in the box today. There will be an example where I put a thing called Hamiltonian variational ansatz, which will work for us in a spin chain setting. And I'll also put a thing which is called ansatz, which will work for my chemistry example, which is quite standard in that context. But again, there's many things, and you need to dive deep to optimize that part. Okay, so I think I already like to go to an example. I prepared 2 cases for today to talk about, and they will fill my time, I think. So the first is going back to spin chains. So I talked a bit like in lecture 2 or so about using spin chains with spin-1/2 qubit, so to say, to build hardware, to make a quantum register. Now I'm going to do the opposite. I'm going to try to contribute to the problem of doing, let's say, the XXX Heisenberg model. And if you wish, I'm going to hunt, the ground state energy thereof, using the VQE method. I'll give you, in a minute, the 1D case, where you all know we can do better, right? We have beta ansatz, and we don't need this kind of procedure to learn things. But then I'll end my lectures, I think, final words of an application in a different domain, 2D Kagome lattice, where we don't know what to do, where we don't have good numerics to this difficult ground state, and where this method could actually help. Okay, but to illustrate how it goes, I will do the 1D chain. So I'm going to give it L sites, and I'm going to try to build a thing like this, to optimize a ground state energy estimate. So now we have to, in a sense, give you what's in the box. And here comes the proposal. I think I'm going to turn the circuit by 90 degrees, if you don't mind. So I'll think from top to bottom. And what I do is I draw my chain over here. So here are my sites. So for some reason I call them 0, 1, 2, etc. And at some point there's site L-1. And then I'm assuming periodic boundary conditions to have the nicest possible situation. So that's where my spin-1/2 sits. And the interaction, just to be sure, they have this here. HXXX is, I guess in my notation, in conventions, this would be like 4s.s. Si, Si plus 1, sum over I. And I put the 4 because in that case, it's actually the sum over I of, x, x plus y, y plus z, z. So this factor of 2 between these 2 things I try to suppress. So this is my Hamiltonian. Here are my sites. So now what am I going to do? So the proposal is the following. So I'm going to build a parameterized state by what's called the brick wall construction. So first step I do is I'm going to put neighboring pairs like this into, let's say, what would be the ground state if there were only 2 sites in the world, right? And I guess you all know, so this, what I write like this here, is the ground state of this problem on two sides, which is the famous singlet. So it would be 0, 1, minus 1, 0 over root 2. So I'm building in a bit of expertise, right? So this, if I get this right, I have maybe a beginning of getting something reasonable. So that's how I start. So I have to do a few things in my circuit to achieve that thing. And then I'm going to put in things with parameters, and that's where the brick wall comes. So I'm going to do 2 qubit gates like this. And that connects to here. There will be a layer, and then there will be a next layer where I alternate my choice of things. And then I keep going like this. Right, so these are the qubit lines. Again, typically they go left to right in these circuits, but today they go bottom to top. So this is qubit number 1, this is qubit number 0, and you get the idea. So that's what we do. Now I should tell you what's in these boxes, in these bricks. And there I'm going to put a thing that I already brought up before, which is this thing we called the Heis gate. With some angle, let's say this is the alpha 2 layer. So here I put Heis alpha 2, here I put Heis alpha 1, etc. And this Heis is in a sense coming from the Hamiltonian itself. So that's why this thing is called HVA, Hamiltonian Variational Ansatz. So it's an ansatz that you kind of build by using the Hamiltonian itself. And there is some logic to why that makes sense, because this is kind of the kind of terms where you hope you can steer the system into its natural ground state. So just to recall, I think I had this on the earlier slides, but so this Heis gate for alpha, so that's a 4x4 matrix on 2 qubits. And I think it's defined like e to the minus I alpha over 4, and then e to the minus I alpha x, let's say I x I plus 1, if it sits on these two lines. Again over 4, yeah. So it's in a sense the unitary for the time evolution of two XXX coupled qubits. So this is just a matrix, right? So let me just write it to be explicit. So it's e to the minus I alpha over 2, and then 0, 0, 0. There's another e to the minus I alpha over 2, 0, 0. And then in the middle sits a rotation cosine alpha over 2. And it is with minus I sine alpha over 2. So this is a unitary which actually was on the blackboard earlier, I think, in the lectures. And so the HVA is simply the statement that you build this circuit, you put in these Heis gates, you give them typically, you can do various things. You can put a new angle for every brick, or you can also put a new angle for every layer. That's cheaper, clearly. So let me follow that procedure. So there would be a same angle down here. And you can keep going. This would be the number 3 layer. So the paper I'm following, so there's layers and cycles. So there's clearly, so this is what my source calls a cycle. And one figure that's important in the procedure is the number of cycles you allow yourself. So the number of cycles is what is typically called P in these papers. And that's also where the costs sit, right? So you need enough P to steer into the ground state with some accuracy, but clearly high P means more gates and more decoherence and more computing time, etc. So let me actually give you my sources. So I'm following to the letter a paper by my colleagues in Amsterdam, Joris Kattenmulle and Jasper van Wezel, which is like half a year old, I think. you know, they did this case as like a warm-up for the actual problem, which is this Kagome story that I'll bring up in the end. So, but warming up for the Kagome Heisenberg magnet situation, they did this 1D version, and I'm using that for my story today. Actually, independently, there was another paper by Bosse and Montanaro with essentially the same proposal. You know, let's do VQE for XXX on the Kagome. That sounds like a wonderful problem to attack using quantum computing resources. So there's these two papers, and they make this very nice story. So but let me, you know, postpone this Kagome story and give you a bit more of this here. Yeah, maybe this is a good moment to go to my demo. I again programmed this thing in Circ, so I can run it in front of your eyes. So can we do this again, Andrea, if you stop that sharing and I share here? I need permission, it's not enabled. Okay, thanks. Yep, so yeah, I hope you can all see that. So here is another one of these little demos that I made. So please be warned that my skills in programming this stuff are extremely basic. So this is all very clumsy, and it's, you know, just the basics of these procedures that I put there. And, you know, there's people who can do a much better job at this. And it's in part on purpose, because I try to explain to you, you know, the first steps of these procedures, and the sophisticated versions are not for here. So actually, I preloaded these things, because in the end there's a few that take a bit of time. So here we go. So I start with the L equal to 4 chain. So that's this thing with only 4 sides, which is nice to begin with. So what I do here, I say I want length 4. I prepare these qubits. I do these operators x, y, z, and then I actually build my Hamiltonian. So I do, you know, a sum of the Pauli times Pauli x, y, and z. And then I print it to be sure that I have the right thing. So, you know, in QPE, I never did this, right? Because I inputted my Hamiltonian via its unitary. Here, I need it because right here, I have to measure all those terms that are over there. So I have to tell my code what that is. So that's ready now. And now let's build circuits. So let's build this circuit. And again, it should be rotated by some angle. So I do this in steps. So the first step I do is to make these bell pairs, so to say. So these spin singlet combinations of neighboring sides, and you know, the circuit that does that is over here. So this H makes a superposition, and then the C naught, you know, makes this combination, and the minus sign comes from putting a Z in the right place. So this little thing does this, and you see I do 0, 1, and I do 1, 2, 3, and that's where my system is periodic. So that's the foundation of my wall, and then. So yeah, okay, so what I can do, if this is my trial state, I can already measure my Hamiltonian, and what you find is -6. Okay, so on a singlet it's -3 in these conventions. So this first effort, if I wouldn't do any layer, would be, you know, estimate -6 for the ground state, which is obviously not the real thing, but this is what's the very first situation. Okay, then I define this Heis gate. So by simply giving the matrix, I did this before in an earlier lecture. I took the same formulas. So, and then I do an even Heis layer, which is, I guess, the one, well, it's one of the two versions. So I do an odd and an even Heisenberg layer. So one does this over here. This is actually a bit silly, because, you know, I should start with an odd one to do something non-trivial. But this is, so you see, you can put these layers, and then the odd one does it in the other direction. And, you know, for example, if I would do this, so I put a layer even, a layer odd, I measure again, outcomes -5. So this is not a very good choice of angles, clearly, because the energy has gone up instead of gone down. So this is just to show that my operators are there. Okay, but now comes the real thing. So now I actually start doing the optimization. So I give myself 2 layers. I call this alpha and beta, and I start with an odd one to be smart. And then you see what this command does. It first makes again these 2 side ground states, like the bell pair states, and then it adds an odd layer, it adds an even layer with alpha and beta. It pulls out the result, and then what it does, it fixes the expectation value of so the expectation of this from the state vector, so to say. And that gives me this number. And then what I do, I have to optimize over angles, and there's, very smart ways to do that. But what I do here is simply, looping over all values. So I give myself 2 loops, I1 in range num step, I2 in range num step, and I simply scan, like a square grid of angle values, and I keep expectation value, and I keep track of which angles gives me the best possible thing. So again, this is extremely clumsy. There's better ways, but this is just for illustration purposes. So here I run this thing, and so here you see my code starts, sampling all these angles and keeping track of the value. It starts at -6, and then for a long time nothing happens, because I guess you need an angle on the odd one to see. And now you see it's actually starting to work. It finds lower values, and it goes and goes and goes, and at some point it's done. And then I print my optimal angles, and I print my corresponding best estimate for the ground state after one first iteration. And you see it outcome 2 angles. There's this one, and the energy is now -7.99. Okay, so I've gone from -6 to -8 almost. And that's only a single layer of my brick wall situation. What I added next is actually I'm trying, so this was like a coarse-grained search, so I added one more step where I repeat the procedure, but I'm kind of zooming in on a small area around my first search result. So I put in the 0.2 pi, 0.3 pi, which was the optimal angles, into a next search, and then I refined by a factor of 10 or so the grid size. So I do it again, run the whole thing, and then come second iteration, new angles that are very similar, and the new energy, which is now -7.9999. And now you probably start seeing what this will converge to. You can actually do this thing by hand. It turns out if you allow yourself 2 layers, you can hit the exact ground state on 4 sides, which is a small system. So this turns out to be good enough. So actually the exact angles to get the ground state are over here. So there's some arc sine of 1/√3 or so. Oh, sorry. Well, arc sine of 1/√3. That's your alpha, and beta like half pi minus that. And that gives you a ground state energy of -8. So -8 is the exact number. And you see my optimizer, actually after 1 step it was very close. After 2 steps, I'm like 10 to the -4 away or so, and it's pretty good. Okay, so that's how this thing works for you. And since the system's so small, a single p equal to 1 cycle does the job, and I'm done. So just, well, to give you a bit more, but this is nothing new. I did 10 sites, to give you a slightly more interesting situation. That's at least 1024 dimensions. So I do the very same thing. So I built Hamiltonian. I built a circuit. So now the initial step has 10 of these things, 5 pairs. I start at -15 for the energy. I do a first iteration, and so this I did at home. I did p equals 2. So I give myself 4 layers, and I simply did the dumb search of scanning the grid. And that gave me a first result, first iteration. I'm here, 4 angles, alpha, beta, gamma, delta, energy down to -17.5 or so. And then I did it again, and then refining it, and then I'm bound down to 17.63, etc. And then I stopped. I could have gone, I may add a few decimal places. I don't know in principle where I should end. I know if I do beta ansatz or ED, but if this is your big problem, this is the situation, right? It's getting better if you keep going, but you don't know how close you are. Just for reference, for the beta ansatz experts, we know, how this energy scales with L, right? That's one of the famous outcomes of beta ansatz for XXX. So we know it's extensive with factor 1 minus 4 log 2. So that's the scaling with L. And if you put that in without any corrections, that number is like minus 70.7 or so. So you see the VQE is approaching that direction. So I think it's, everything is correctly done. I'm getting close, but I'm obviously a bit away from it. And actually, I asked Jasper from Joris Kattemüller yesterday, do you know how many layers you need for the 10-side situation to still be exact? And the answer is 9. So you need p equals 9, meaning 18 brick layers to act on the head. So less than that, you will approximate, but you won't be exact. That's life. That's how VQE works. You probably get really close, but you don't hit it. And I think it's like a theorem that if you give yourself enough layers, you can always do it exactly. But that number is going through the roof very quickly. And in practice, you don't have that capacity, so you do a certain number of layers and then you stop. So actually, in the paper, so that's sort of, I guess, yeah, this can go. The notebook stops here. I'll share it with you again after the lecture, so you can play with it yourself if you like. So I stop share. Maybe can you put me back on the screen? Then I have sort of a last remark about this procedure. So because again, these authors, they did this in professional fashion, where they explored much more than what I do here in my toy implementation. And there's one sort of thing which is nice to show, I think. So the paper of Kattemüller et al., they showed the L equals 20 case, some data they have for doing that. And so they made a plot of, on this axis, I think what they call the relative error, so there's some epsilon, which is like E minus E ground state over a reference value, which is the thing you want to be low. And I think on their plot it's like, so somewhere here is 10 to the minus 2. And then the plot goes down to like 10 to the minus 5 or so. And then on the horizontal axis they put the p, so the number of cycles they run to do this. So that's like p equals 2, 4, 6, etc. So this is the p. And clearly what you expect is that this error goes down if you give yourself more p's, right? That's the whole idea. It can never go up, because if you add an extra set of angles for next layer, you at least do as good as without that extra layer. But now comes the outcome of, so I'm sketching a graph from their paper, which is kind of like this. So yeah, maybe I'm exaggerating a bit, but it's clear, so the accuracy is improving with p, and then there's a certain dramatic improvement around p equal to 5 here. And there's a reason for that, so that's why I bring this up as a nice illustration. Can anybody see why p equals 5 is the magic value? Right, that's important. So this is my chain, right? It has 20 sides. And we know the ground state we're after is, a highly entangled, critical many-body state. So the least it should do is entangle, everybody with everybody else. So if this is my site I equal to 0, and this is my site I equal to, 9 or so, then I should, in my ground state, I should have entangled these two guys, among other things. But, what my brick wall circuit does is entangles, first, 0 is 1. Next layer, it entangles 1 with 2, 2 with 3. And it actually takes me, 10 layers to reach 9, so to say. And 10 layers means 5, p equal to 5, in the way I count. So you can imagine, by the time you've given yourself p equal to 5, 10 layers, you've kind of gone around the system and everybody has had a chance to untangle with everybody else. and you can expect improvement, right? And that's exactly what happens. As soon as you pass that point, then the accuracy goes down quite fast, and the thing has sort of scrambled to become a realistic candidate for the ground state. So I think that's quite nice, right? That's some clear intuition why this works. And in the 2D version for Kagome, something similar happens. You have to do enough layers to entangle everybody with everybody else in the system. So my example was too small to see this effect, but here you can actually see it quite nicely. Yeah.
So, well, you said it became exact for p equals 9. Is there also a...
That was for 10 sides.
Okay, and for 20
yes.
sides, how many?
I think they don't know.
Okay.
I think I was offered to figure it out for 12, and then that's where it becomes difficult.
Okay. So there's no simple argument to see when it becomes exact?
No, actually, I'm intrigued by that question. So I've also been discussing with Yuan, can we somehow do some kind of version of beta ansatz, algebraic beta ansatz, built on this, so based on this ansatz, right? So is there a pattern to the angles alpha that produce the exact ground state in this parameterization? It feels like there's something there, but it's a bit hard. If you try to do exact stuff, you have to commute these Heis operators among themselves, and that's a big mess. And it's not clear how to control that. Yeah, but I think it's a beautiful thing. I mean, there's many variations of circuits of this type, right? There's Rule 54 and all kinds of quantum circuits that look a bit like this and that have magical properties. So that's a nice area to explore. But I think for now this was enough on this topic. Yeah, let me maybe start my second example, which is sort of an extensive example. So I do a bit of that, and then we can break for coffee. So that's the quantum chemistry context, which I think is really nice. And it's in a sense a situation where this whole procedure is really in place, and where it works for you in a very nice way. But there's also, it needs quite a bit of introduction, at least from where I come from, to understand what these people are doing in quantum chemistry and how they use this in a practical way. So, but I decided to take like my last hour of lecturing time to go into this, because I think it's really beautiful, and and everything you do there, you can kind of translate to doing, for example, your favorite Fermi-Hubbard model or something like that with very similar methods. So you could also pull this in the direction of materials and quantum matter, etc. But let me kind of try to adopt some chemistry language. I'll be using all kind of abbreviations which I have to learn myself, like STONG, 631G, PVDZ basis, etc. But let me come to that. So let's, look at what I like to call QC squared, quantum computing for quantum chemistry. Let's imagine, this is talking about molecules typically. And just, I know you've all seen these things before, but let me give you sort of the Hamiltonian, that's going to do the job. You all know what that is. It's Coulomb interactions for particles moving around, etc. But just to be precise, so there's a bunch of nuclei with some charge. So let's say Z, and I use capital I for the nuclei, and there's a bunch of electrons. Right. So and that's the electrons E sub I. I typically goes from 1 to N, and capital I always goes from 1 to K for nucleus. And then the Hamiltonian that does it all, so, which is the precise thing we are going to try to minimize in many, many steps. Well, you know what that is. It's the kinetic term for all the electrons. So I'm putting lots of things equal to 1 or half or so with a minus. It is the interaction, Coulomb interaction between electrons and nuclei, which is going by the Z strength, and then it's the Xi minus Xi squared. Sorry, not squared, this is an energy. And then there's the electron to electron terms, sum I unequal to j, 1 over xi minus xj. Okay, so just, again, I'm sure you've seen this before. This is already not the exact thing, and you know that. I'm only talking the sort of dynamical electrons. So what I've done is what's called Born-Oppenheimer approximation, where I'm assuming that my nuclei are fixed in space. So there's no kinetic energy for them. And this you justify by the fact that these things are much more heavy than the electrons. You've all heard this story before. So this is the problem. Find the ground state energy for this Hamiltonian here. Okay, so let's try to make a start handling this thing, and you can think about your favorite molecule as we go. In the end, I'll zoom in on H2, which is the obvious, simplest thing to consider, but I'll postpone doing that for a bit. So the first thing to work with this, this is complicated stuff. These are the wave functions this thing acts on are, continuous 3D, etc. So this is by far a discrete problem that you can put on a few qubit lines. To go in that direction, you need, a basis set. A basis set for your wave functions. Orbitals, if you wish. Okay? And typically these are written like, there's some phi, I label them with index p, and they depend on 3D space. And I typically give myself m of these. Standard notation in this field. The p actually hides spin, so typically I would have spin up orbitals and spin down orbitals. But for now, the rotation is like this. And this is actually where the choice of what you do here is extremely important. I guess you can feel that, right? This is a continuous space problem, depending on wave functions, psi of x1, x2, etc. I'm going to try to kind of decompose these wave functions on a small basis set. And clearly, if I make a clumsy choice here, I'll never get good accuracy in my answers. So this is really important, and this is also like an art in the chemistry world of how you do this thing, and that's where all these abbreviations come from. So for example, a choice of orbital is Slater type orbitals that you actually build using n Gaussians. So that is STONG notation, which is nice for the start, but it's not good enough, I'm told, to be accurate. That's clear. And then there's all kinds of things. So for this H2 context, 631G is a choice where you kind of double the number of orbitals as compared to here. And then there's this polarization thing with double zetas and what have you. And clearly, if you allow yourself more p's, a bigger list of orbitals, you can do better. Right? You have a more fine-grained basis to decompose the actual wave functions on. So this is really an important thing, what you choose here. And I guess depending on how much your hardware can handle, you try to take a rich basis rather than a simple one. Now having done this, it's actually, you can rework this Hamiltonian essentially on that basis. That you would know how to do that. And just to give you one step, so I can define HPQ, which is sort of the two body terms in here, or the one electron terms, I guess. So I would simply sandwich that part of the Hamiltonian, so the minus grad squared and the electron to nucleus interactions. So for one electron, it meets a bunch of ions, so to say. So there's x minus xi. And then I'm simply doing, an inner product of my orbital phi star of x, and I put phi q over here of x, and I do a dx, and I think that's it. This gives me a number, and that number I call HPQ. Yep. And then I can do a similar number, but involving 4 orbitals, PQRS, which I'm not going to write, but that's actually, sandwiching this thing, which has 2 electron coordinates, so I need a pair of orbitals, 5 star 5 for both. Gives me this thing here. What I can then do is, set up some second quantized notation. So I'm going to introduce creation and annihilation operators, which I think in physics we will call C, fermionic creation and annihilation operators, but in chemistry these are called A for some reason. So there will be A dagger P's and A Q's and stuff like that, with the canonical anti-commutation relation. So those operators, they load an electron into one of these orbitals. The A dagger P loads a particle into this here. And if you've done all that, I guess you will agree with me, the Hamiltonian takes on a form which is a lot simpler now. It looks like some PQ, HPQ, A dagger P AQ, plus quartic term PQRS, H PQRS, A dagger P, A dagger Q, AR, AS. Okay, so now it's a lot nicer, I guess. It's a lot easier. It's only m by, so it's not m by m, but it's now concerning, putting n particles and electrons into m orbitals. So I guess the dimension that we're talking about now is this, right? It's binomial m of n. This is the dimension of how many terms are in this Hilbert space. And the Hamiltonian is just a matrix of this size, given over here. And my task is to diagonalize this matrix and find this ground state, which is, a lot closer to a discrete problem we can handle. So I think, I'll handle this after the break, but just let me stress a few things. So first of all, coming here, we needed to make choices, right? We had to choose. So this was almost exact up to Born-Oppenheimer, but then choosing a basis and doing it like this is sort of, coarse graining the Hamiltonian from an actual 3D wave function depending on x to a discrete thing that we can expand on like this. So this you need to do, and again, the art is to make a good choice of orbitals, but with as low as possible number of them, because clearly this m, so the m over here, sits down here, with big powers. And if you compute how expensive your circuits are for doing, let's say, VQE, you get lots of powers of m. And if you allow yourself a big m, that means big cost in the circuit. So you want to be low m, but you want to be as accurate as you can, and then that lands you here. This almost looks like a thing we can put on a qubit system, but mind you, these are fermionic operators, because we're talking electrons. So there is a step to be taken, which I haven't done yet, to map from fermions to qubits, during a week or so. So that will come later. And then we can talk about how we do this with the VQE approach, or if you wish, a QPE, but for today it will be a VQE approach. Yeah, so I think that's a nice moment to break. So after the coffee, I'll go a bit into this, do an example, and give you, in the end, the circuit that handles in this approximation. Okay, so I pick up my story from here. We did some preliminary things to put, let's say, a typical chemistry molecule problem in a form we can start to handle with quantum computing. So the intermediate result is this form of Hamiltonian over here. So there's the pre-processing steps that I mentioned, starting from the real thing, choosing orbital bases, etc., leads to this discrete Hamiltonian. It's still too big to do in ED. Well, only small size things can be done there. So the idea is to do it in variational calculus. And again, the art is to find a for that. Because if you do a blind search in a space that's as big as this here, you'll never hit the goal, so to say. So let me try to give you the strategy, which is quite standard in the chemistry world. So there's like 2 steps. Step 1 is a Hartree-Fock step, and then step 2 will be an improvement thereof. because Hartree-Fock mean field, that will not be good enough. And that, there's various ways to do this, but what I'll pick today is this unitary coupled cluster ansatz on top of Hartree-Fock. Okay, so let's see. In this basis with second quantized formulas for orbitals, I guess we can describe like a basis of the many-body states by simply giving occupation numbers, right? So I could specify, I do it like this. If I have m equal to 6 or so, and that is a basis factor of the many-body space of this, where this thing H is acting. And what you see here that so what you have is that this type of thing, there's n of those are the occupied orbitals. I need one per electron, and then everybody else is what's called the virtual orbitals, or the unoccupied orbitals. Okay, so now the first thing you can try to do is approximate the ground state with a single one of these, a single basis factor of the many-body room. Now, if you take the basis that we came from, this is probably not going to be very good. But the idea is you can allow yourself let's say one orbital rotation matrices, right? So you can imagine rotating in this space of all these 5 sub-p's in such a way that a state like this is going to be a low energy state. So the idea is you settle for a single Slater determinant as your ground state, but a term of optimized orbitals. Quantization that would look like this, or maybe let's say slightly easier, it would look like this, right? So you rotate, so you do like you optimize the 5p basis, so to say, again by allowing yourself rotations in space, such that filling the first so many of them and leaving the rest empty in second quantized notation, or building a Slater determinant in first quantized notation, is your approximate ground state. And there's a well-known procedure for optimizing this. So optimize what you do here to find the best possible result. That's called Hartree-Fock procedure, and that leads you to an approximate state. Let's call that psi Hartree-Fock. And it really pays to do this first, right? Rather than start with other things, because this captures a lot of the correlations in the system by a relatively simple step. So that's step 1. But then again, it won't be good enough. And now comes this step 2, this coupled cluster expansion, which is a way to actually build on top of the Hartree-Fock state. And the formula that goes with that, so my step 2 is here. So there's CC and UCC. U is for unitary. It's the following proposal. So we're going to consider states of the form psi CC, which we build from psi HF by doing some unitary rotations, e to the t, where t is anti-Hermitian, so this thing is unitary. And what I take for t is a sum of terms, let's say L equal to 1 and 2, etc. And then I do a TL minus a TL dagger. So by doing this, I'm guaranteeing it's anti-Hermitian. So my thing is unitary. I guess I need an I somewhere, but you get the idea. And then what these T's are, there's a T1 and there's a T2, etc. These are operators that act on a state like this, which is my Hartree-Fock reference state, and they put, if you wish, a particle high excitation. That would be the physics language. So you take out one of the occupied electrons and you put it in an empty orbital. So the notation would be, T1, I do this once, so I do like a sum over Ti alpha, so I destroy so the alpha, I pick one of the occupied orbitals. For the I pick one of the virtual orbitals. And I simply put my particle from here to there, and I give it some angle, if you wish, some parameter in front. So that's T1, and then T2 is the same thing, but doing it with 2 particles. So now there's an alpha and a beta in occupied, and there's an I and a J in empty, in virtual, and I do T, IJ alpha beta, and I do A dagger AA with alpha beta IJ. So it's a rather obvious thing to do, but you know, it turns out to give an answer that works. That's going to steer you in a corner of Hilbert space where you know you're coming much closer to the ground state. Okay, and actually, so one more abbreviation. So chemists like to call this thing the singles and this the doubles for obvious reasons. And if you stop the ansatz after L equal to 2, which is most of the case done, it actually goes under the name unitary coupled cluster single double. So if you like to impress your friends with lots of abbreviations, this is a nice one. Unitary coupled cluster single double. And you know, in the language of today's story, clearly this thing here is kind of, there's some variational procedure, but that's done, right? So Hartree-Fock, that's a known thing that you do, which is not very difficult, and that gives you the optimal choice of that. But here are variational parameters. So these T's, these are my, if you wish, my angles for the ansatz. So these would be like the theta 1 to theta s. Ti alpha and Tij alpha beta, etc. So this is the corner where you find these things and where you build your trial state. So this is very general. Let me at this moment, zoom in on an example and actually do it, right? I'll analyze an example, tell you what the Hartree-Fock states are, how this thing looks like, and then in the end give you the circuit that I should run to do my VQE. So just to be completely explicit, I thought that would be nice. I didn't code it on Circ, but I think there would be one small step to add if you are interested in playing with it. So the example, as I already mentioned, is the H2 molecule, which is like the fruit fly of this business. In a sense, what I do is overkill. I guess you've all learned in your quantum physics 2 course or so how you do variational analysis for this situation. At least I learned this from the Griffith book, and it doesn't need all this language. But let's do the example. So you probably recognize what you learned in school in this formulation. Then you'll see how to lift it to bigger molecules, where this formalism is really nicely designed. So H2, you know what that is? It has 2 nuclei. It has 2 electrons. Maybe before going into the formalism, let me recall you, how the essence of this problem, right? So what you typically do is you assume these, Born Oppenheimer, so these 2 protons that make H2 are nailed in space. What's interesting is how far away they are. So there's some radius r, which you don't know. And then, what you typically do is you solve the 2 electron problem in this background. So you put 2 electrons, number 1 and number 2, and you do the 2 electron problem with that Hamiltonian, which you cannot do exactly, by the way. It's already a too difficult problem to handle analytically. And what you do is you compute the ground state energy in variational calculus, or ED if you wish, as a function of R. And what you then find, there's, this is energy 0. What you know is that if you make R really big, what you find is twice, minus 13.6 electron volts. So that's some kind of asymptote where for a really large R, you're going to find yourself. So that's what the chemists call 1 Hartree. That's, 1 Hartree is twice the hydrogen ground state energy. But then, what you find is that the optimal energy does something like this. So that's what comes out of these analyses, and this is tells you what the physics is, if you use the chemistry. Namely, nature will settle for this radius r sub 0, which comes out as about 0.75 angstroms, and there will be a binding energy to this molecule, which is like this, right? So pulling the 2 H's apart to infinity costs you this much energy which is a few electron volts, and that's the binding energy of the H2 molecule as compared to two, individual H1 atoms. Okay, and again, what you like to know is two things. You want to know this R, and you want to know this delta E, so to say, delta E. And in a sense, this is like the cartoon. If you do a bigger molecule where it's much more difficult, there's again a situation of where are the ions, distance, angles, etc. And then for each choice of, let's say, the classical geometry of your ions, you do the many electron problem and you discover the best energy, and you can make all these plots. And doing all this, you can, for example, figure how chemical reactions work, right? Which path they follow in configuration space. But this is like the baby example for that. Okay, so this is the quick story, but in a sense, we are supposed to reproduce this thing using our quantum computing machinery. Okay, question?
Yeah, very super basic questions. So this, when you plot the energy here, so it's the energy of the Hamiltonian you wrote on top. So
yeah, we read this thing here.
Yeah.
So it's the thing that gives you minus 13.6 electron volts for one electron.
Does it include also the nuclei Coulomb?
Yeah, sorry, yeah, very good point. That should be included to get this right. Yeah.
So you put it on top of the...
Yes, so the plot is actually for the H total, which is my H electron, which I give over there, plus H nucleus. And it matters, right, because this is also R dependent. So sorry, I forgot to say that, but that's important. It's a classical term, but you should add it by hand. Okay, thanks for the question. Okay, so this is what we expect to rediscover today. But let's do it, following that kind of language. And again, it's a bit of maybe overkill, but I think it's nice to see how this happens. So first step in the procedure, we should take a basis set for this problem. And actually, so I think in the jargon, we go for a thing called STO3G, which is simply, one orbital describing, let's say, the 1s electron state in the first atom, which we call A today, for spin up. Okay, so that's, let's say, the S1 orbital for this hydrogen atom on the left. So this is called A today, and this is going to be called B. And then what you do, clearly you need the 1SA down. You need the 1SB up, and you need the 1SB down, and that's it. So I'm going to take a single orbital for each of those. That's the minimum I should allow myself. So it's an m equal to 4 choice. That's not too bad, right? So the m that's over there, I take 4, and my whole problem is going to be to put 2 electrons in 4 of these orbitals. So I'm down to, I guess, a 6 by 6 problem, if you wish. So yeah, that's the first thing. At this point, I can actually run the machine and compute these H's. So that's kind of mindless processing, right? This is just doing integrals and outcome some numbers. Maybe let me give you that. Sorry, where? Let me see where I put that. Yeah, so let me put that here. So if you, no, this is too early. Let me not do that. So let me, I guess these things can be done, but let me postpone a bit writing that. To keep my story aligned. So let me actually try to, where do I go? Maybe go here. So let me talk about the variational ansatz, and let me postpone translating to qubits for later. Yes?
Yes, a question. So this minimum is chemical bond energy, bonding energy, is due to the exchange term in the Hamiltonian, or?
I guess, yeah. I guess it's in the end these terms that do it, right? So if I'm very naive, I could say the electrons tend to kind of locate a bit in the middle between the two protons, so that the sum of the Coulomb energies is favorable. Mm-hmm. But that's a very naive picture. Mm-hmm. But okay, in the end, it's the Coulomb energy that does it, right? That's what binds the stuff together.
So it's all in the symmetric orbitals. No excitation. No. Okay. No. In fact. Okay. No. Okay.
Well, because that's what we have to discover, right? So these four things have to build up the state, and this coming. So there will be symmetric, and antisymmetric. But let's do that. This is actually precisely the analysis that's following. So that's
sorry, but the exact ground state is not really built out of that four. I mean, the exact one.
No, I think even no, we don't have the two-body function in closed form. I think it's a non-analytic thing. No, nobody has that. Clearly, you can do very good numerics, and we know all the digits, but it's already beyond analytic control. It's this Griffiths quantum physics books that we always teach from, and so it has all these exact things, harmonic oscillator and that in the early chapters, and then they talk about the real world, and the first thing you hit, you cannot do. And then the next thing you also cannot do. You cannot do the helium problem, right? Because the electrons are having a Coulomb interaction. So I found that rather shocking when learning all this. But okay, so let's go through the procedure. And I told you to build the ansatz. One thing we should at some point do is translate to qubits, because we're still talking fermions. And the other thing we should work out this Hartree-Fock plus coupled cluster ansatz. So let's do that first. So if you do the Hartree-Fock step, meaning you optimize combination of orbitals that you can then fill to make the best state, that's a rather obvious thing because the system is so small. The optimal orbitals are like this. So there's a sigma g up, which is 1 over some number, which is it's not 1 over root 2, it's a different number, and sub g of, and now I take the s, the 1sa up orbital, and I add the 1s the b up orbital, right? This is a spin up orbital, and well, let me put so there's some order. So there's also the gerade for down, and then I can do the ungerade for up, and I can do the ungerade for down. So somebody, these chemists like to talk German, right? So we call this even odd. They call this gerade, ungerade. But it's the obvious thing. So you combine these things for spin up, spin down, and the gerade means there's a plus here, and ungerade means there's a minus here. So it's the symmetric, antisymmetric, or the binding, unbinding orbitals, what have you. So it turns out this is what Hartree-Fock gives you for this very simple problem. By the way, this is not 1 over root 2 because there's an overlap of these orbitals. So these wave functions, the STO3G, they have a shape in space. And if I put one around atom A, another around atom B, there's an overlap. And for normalizing the state, I need to know that. So this is a difficult number. It's not 1 over root 2. Okay, so this is my choice of basis in Hartree-Fock. And so having done this now, I guess let me keep writing big font. So let me make room here. So on this, Hartree-Fock basis, I can write, whatever state I want as a psi in this basis. And what I do is I'll specify occupation numbers of these 4 things. And somehow I have to choose an order, and the order I choose is I put here the ungerade down, here I put the ungerade up, here I put the gerade down and the gerade up. So these f's are all 0 or 1, clearly. So this gives me 16 dimensions, which is is that true? Yeah. 16 dimensions, but if I insist on 2 electrons, it's only 6 dimensions, right? I can arrange 6 things. And now comes the factor, the Hartree-Fock state in this basis notation. So you achieve, as a single Slater determinant of those orbitals. Namely, what you do, you fill the gerade and you leave the ungerade empty, right? So you use the GG. So in this notation, it would look like 0, 0, 1, 1. So this is not qubit language. This is still, fermionic creation operator language. I'm stressing that because there will be some minus signs we have to deal with later. So this is, Hartree-Fock in this basis, and it's, as a wave function, a Slater determinant of those 2 top orbitals. And that's what you have. Again, it's not good enough, so we'll enrich this ansatz. It's not an ansatz, this is just an intermediate result. So we'll still have to build the ansatz, the coupled cluster ansatz. But that's coming. I guess this is a good moment now to actually switch notation, from fermion to qubit. So this thing called, well, one way to do that is called Jordan-Wigner. There's other ways to do it as well. I think for nobody in this audience, this is a surprising thing. So what you do, you define operators on the qubit language, which are my Pauli x and y like this. So there's a q and a q dagger. So this is qubit operators, and then you can make like a translation from electron operators, these A's, these guys here, fermion operators, to qubit operators by saying the following. So here's a little table for doing that. If I want A0, so that's the, so actually I label these locations as 0, 1, 2, 3. So if I want A0, that's simply Q0. But if I want A1, then the logic in this conventions is that the operator taking out the electron at location 1 has to jump over the one at location 0, comes from the right. So it picks up a phase from that. So there's a Q1 Z0, which can be a minus sign. A2 is going to be Q2 Z1 Z0. And A3 is going to be Q3 Z2 Z1 Z0. Okay, so this is a way to guarantee that the bosonic qubit operators x, y, z, as we know them, that are here, are made to anti-commute canonically and represent fermions. Right? So I guess everybody has seen this one way or the other before. This you can do. There's actually other ways to do this. There's a thing called Bravi-Kitaev, which is a different way of doing this, which is sometimes better. I think for this problem, it gives you less terms. So in that sense, it's a bit better. And there's still more ways, but let's stick to JW right here. Okay, if I've done that, so now I know exactly how to write A's in terms of qubit operators. So at that moment, I can actually write this guy in terms of qubit operators. So I simply insert for A dagger and A what I have here. And I get, a whole load of Pauli x, y, z, but I can simply do it. And so I get a formulation now of my Hamiltonian. So having done this, so the Hamiltonian, let's say in the qubit language, maybe call it like this, H2 qubit language. So I'm not going to write it in too much detail, but what you get, it looks like some H0 times the 1 operator, and H1 times the X, so the Z0 operator, and H2 times the Z1 operator, dot, 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 lots of terms. There's an H5 times Z0, Z1, lots of terms, and the final one is H14, X0, X1, Y2, Y3, whatever. Okay, so out comes some expression that you simply pull out by doing this. So that's a thing to keep in mind. We need this operator to run the VQE when our ansatz is all done. Yeah, I'm almost there. The one thing I should still do is work on the ansatz. This was an intermediate step, the Hartree-Fock. I told you to go to the unitary coupled cluster single double. We need to, you know, to add this U on top of Hartree-Fock, which is e to the T1 minus T1 dagger, and e to the T2 minus T2 dagger. So now let's, you know, zoom into our situation. What are these T1s? Well, T1s are supposed to take out a particle from the occupied bunch, which are the two gerade orbitals, and, you know, put it back in an empty one, which are the ungerade orbitals. And, you know, since you want to do the whole thing in the z equal to 0 subspace, you're looking for a state like that. There's not too many options, so you can do like A2 dagger A0, so meaning you jump from here to here, or you can do from there to there, which is A3 dagger A1. So those are your options. And for the T2 terms, the only thing you can do is, you know, do a dagger of 3 and 2 and take out 1 and 0. You know, since I've only two particles, the double ansatz is where it stops. So now this looks like a bit complicated, and it looks like I have at least 3 angles. If you look at these guys here, they're not really needed in this situation, right? They would actually, so they would be taking out a G, putting back a U. In a sense, that would mean I'm rotating I'm rotating a back again in that space between the G and the U directions, and I already optimized that in my Hartree-Fock. So in this very simple setting, this step here is kind of done. It doesn't materialize into anything new. So let's forget about that. The step down here is actually non-trivial. So what you should do at this point, you know, is put in the vocabulary of Jordan-Wigner into this expression and generate a Pauli string word. So that's a bunch of terms. But again, you can simplify and make your life a bit easier. And what comes out in the end is that this U is for the double part, it's a simple operator. So the U looks like e to the minus I theta, where so theta is this coefficient of this term here. And then it's a thing x3, x2, x1, y0. So I think this is kind of natural, right? So what this thing does, it flips, you know, 0011 into 1100. So it flips the GG state to the UU state. And to do that, you need flip operators, and there's x's and y's, and for some reason, the things come out like this here. So that's the unitary U that sits in this ansatz. And if you now finally, so let me put that in this corner here. So the U we've seen. So finally, this leads me to my trial state. If I implement this operator, which is the psi trial of angle theta. So that's my variational parameter. So it's the U of the 0011. So right, it's the coupled cluster expansion on top of Hartree-Fock. That's what we should do. And the way it looks, you know, it's simply cosine theta times where we came from, and it's sine theta times the other guy, and there's actually a minus sign here. So there's not an I, that's good, but there's a minus sign. And that's because, you know, we put a Y here. So the usual minus sign, the usual minus I is now a minus 1. So this is the ansatz state. Okay. So that was a lot of work. But this is what we get. And you see it's like a one parameter ansatz. So if I give myself as little room as I did with only 4 orbitals, then, you know, if I eliminate symmetries and then all these things, it's down to, if you wish, a 2D problem. So there's the obvious Hartree-Fock, the GG, but then the actual thing will have a bit of UU in there. So I think, yeah. So I'm almost ready to run the VQE, but the best state in this ansatz will be have a non-trivial theta. So the ground state, the physical thing that builds up in the H2 molecule is of this shape here, given my small size basis set. Yeah, so I'm almost there. So now finally let me give you my circuit. Yeah, I have enough time to do that. So it's maybe, again, I'm a bit overdoing it. If you wish, you're down to a 2D problem here, and you can evaluate the energies as a 2x2 matrix and do it from there. But if I stick to the notation that I kind of built by following the natural procedure, I'm still in this space spanned by 4 qubits, and this operator is actually acting on 4 qubits because it has all these lines. Right, so I should build a circuit that has 4 qubits to do this procedure without cutting too many corners. So yeah, let me do that. So I guess our little task is now to write a quantum circuit for the operator that's over there, e to the minus I times theta times x3, x2, x1, y0. So that's going to be the black box of the earlier drawing. And just for fun, let me show you how that looks. It's kind of a funny thing. So I have the 4 qubit lines going into this. So there's I guess it's the 0, 1, 2, 3. As I label them, giving me, referring to those 4 basis states. Right? So I'm labeling these guys as 0, 1, 2, 3. And each have their own qubit. The Hartree-Fock state is, 1, 1, 0, 0 in this basis. And the rotation that I need to implement, this U for my ansatz, is, it's a 4 qubit operator. Let me give you intuition how you handle this. This is exponents of x's and y's. That's difficult. It pays to go to a basis where it's exponents of z's, which are easy. So for that you need to make a base transformation. Go from x to z. That's a Hadamard. So let's put that first. Let me not draw the boxes. So Hadamard, Hadamard, Hadamard. For the y to z, that's a different matrix that looks like Hadamard but has a few i's here and there. That's typically written as Rx of pi over 2. So a rotation of the x direction. So that's how I begin and how I end. So when I'm done with my rotation, I'll put these same guys inverse. So I guess here minus pi over 2. And here Hadamard, Hadamard, Hadamard. And this means that in the middle of the circuit that I'm trying to discover, what I should really do is not do this U, but do this U. U to the U, sorry, the U in the middle is going to be e to the, I think it's a plus now, I theta Z1, Z3, Z2, Z1, Z0. So now I have to do that. It's easy to do an e to the z. For example, if I can put on this line down here, I can put e to the I theta z. That would take care of this guy, right? I could put the same thing on the other lines, but that would not give me this. It would give me this with pluses and not products. And actually, if you think about how you achieve the product, you have to entangle these guys with a whole bunch of C-naughts. So the circuit that actually does this thing quite nicely is like this. So you make like a cascade of C-naught gates, which you undo when you're done with your sorry. I need one here, I need one here, and then I need one here, sorry. So this will be on my circuit. So it looks a bit like this thing I started my lecture today, though, and ended yesterday. You know, it's compiling this kind of coupled rotations into single rotations, so they're happening down here, but then with a bunch of C-nodes to make sure everybody co-rotates, so to say, while doing this, and then all these basis transforming bits and the you know, on the side. So this is the circuit that should do it. So here's the e to the I z theta on that line. This, you know, this is just a fun thing to figure that out, but let me give you the conclusion. So this black box, you know, is the thing that fits in my circuit that I started my whole discussion with. So this is what makes, you know, the psi. So if I simply input the 0, 0, 0, 0 on this, or the Hartree-Fock on this, so the 1, 1, 0, 0, that's where I start from, that's the Hartree-Fock. And then this makes me the trial wave function as a function of a single angle, in this case, theta, which, you know, which goes in here, and which is then, you know, shared by all the other lines to be this operator, and the end to be that operator. So that's, you know, what we can do. And then to complete the circuit, you know, we put the measurement block, you know, where we put all these, where are they? These 14 Pauli words, you know, one by one on this here. So this is the measure, the block that, you know, measures the H2 in the qubit version. So again, it means to do one run, you have to do 14 times the circuit and the term and the measurement, and then you pick up the values for all these terms, you add them up, and that's the energy for that trial. You know, so you pick a theta, you do all this, you have an energy, you try the next theta, you get a better value, and then you optimize, and that gives you the final answer. Okay, and for example, to be completely explicit, so what I learned from the books is that if you actually put in all the numbers, so the honest hydrogen numbers, and you run this thing at the optimal radius, so this 0.75 angstroms, you know, what comes out is a state. So the optimal thing that's finally produced by this is a state, you know, which is 0.9939 times the 001, and it's the other one. So there's a bit of mixture, minus 0.1106 times the 1100. So the ungerade, you know, blends in with a small weight of about 0.1 at the optimal position. And if you have this and you process Hamiltonian, you know this binding energy that you were after. And then you've, I guess, completed the procedure. Okay, so it's, you know, as I said, it's a bit too much for this simple problem, but it gives you the road to get there. And if now your next problem is a bit bigger, you follow the exact same steps, and you'll run a VQE and learn a few things. And again, this is what the people in chemistry do. So all the work they do is, you know, optimizing bits and pieces of this procedure. So picking better orbitals, being smart about how you build this thing, being smart about the optimizer cycle, and all these things. And it's a big thing to get right. Which brings me to the final thing. As I said, final words. I already mentioned that, and I don't have too much else to say. But this idea of Kattenmüller and co-workers and Montanaro and co-workers to actually use a VQE for something new in physics. So let's, let the chemistry rest for now. Back to the physics, and so there's this idea. There's in general in quantum computing, people are searching for a nice problem where quantum computing helps and makes the difference and improves classical computing. And that's, let's say, interesting and tractable, all these things. And we don't have that yet, right? There's a claim for quantum supremacy, which is actually, debated. And even if it holds, it's not an interesting application. It's just sort of a crazy problem where a quantum circuit could do something that's not tractable for us. But that's the idea. Can we do a quantum many-body problem that's interesting, that we would like to know about, and that kind of fits in a good way on quantum hardware? So that's this thing. There's this phrase. Can we have a problem with a hardware-efficient ansatz? So meaning that it's an ansatz that doesn't require too much compiling, so that the circuits stay small, and we can actually hope to make progress. And so the reasoning that I picked up from talking to Joris and the guys is that, well, the first thing, if you try to be efficient, try to avoid all these minus signs that fermions come with, because they require difficult mappings. And in 1D it's not so bad, I gave you what it takes, but in 2D it's bad. Like a Jordan-Wigton in 2D is with snakes and stuff is complicated. So let's do a bosomic problem, and then, let's do a spin problem. To spin a half. I gave you the 1D chain, but that's not so interesting because we can handle that with other means. But the proposal that these two groups independently arrived at, let's do, the XXX magnet, the antiferromagnet, so I guess the AF, the antiferromagnet problem on this Kagome lattice. And the reason from the physics side being that this is a famous tricky business. So the many-body state that is the ground state for this thing here is frustrated. It's very hard to nail using tensor networks or Monte Carlo or what have you. So there's, as far as I understand, there's still question marks on exactly what is going on here, what this state is. So that's a good motivation. And then the next thing, this hardware efficient means that the gates that the hardware allows you to have are exactly what goes into the ansatz, right? So that there's not too much compiling. And the thing is, if you go to, let's say, superconducting qubit platforms, the types that Google and IBM built, that have rather big sizes. So what I understand is that building, for example, this Heis alpha gate is relatively easy on that hardware. So there are some native gates coming with superconducting qubits. They're not exactly of the XXX type, but it's not so bad. So this is relatively efficient on let's say, the superconducting qubit platforms. So that's good. And what's also good is that the geometry of Kagome is a 2D grid. The geometry of the hardware is typically 2D grids as well, square lattice or something like it. So it's relatively easy to, to program, so to say, moves, Heis alpha moves on the grid of the qubits, so that they actually mimic the Kagome situation. So the idea would be that actually somebody builds, a superconducting qubit platform that's laid out in the Kagome lattice shape. That would be perfect. Then there's kind of zero complications. But what is available, what is built for other reasons with sort of 2D square grids is quite close. And these two papers explain how you actually go from one to the other without too many complications. For example, if your qubits would be on a line, right? And you would imagine going after the VQE for 2D Kagome, that would be terrible. Because then you would have to translate all the time between nearest neighbor relation on the line and on the Kagome, which would give you loads of swap gates to do, which are expensive. So that's a bad option. But if the qubits come in this 2D layout, it's not such a big step to actually translate what you need to do to the Kagome. And so in that sense, sort of all the complications that come in this kind of proposed VQEs are relatively mild in this situation. So there's no fermions, no minus signs. The gates are pretty much native, and the geometry that you're targeting is rather close to the geometry that you have available. So in that sense, this is as good as it can be. And so what these people argue is that, putting this Kagome, so the version of what I showed you for the chain, the version for the 2D Kagome, putting that on the actual hardware could be a nice place to start looking for a quantum advantage of this type. And so I'd like to, echo that message. And, so, and then, the other thing that I wanted to say is that, yeah, I think that would be my final words for my story. So we started with looking at hardware, we ended with looking at applications of that hardware for doing many-body physics. And I think it's a beautiful business that's unrolling as we speak. So thanks for listening.
Questions?
Sorry, this is a 2 + 1 dimensional system, right? This is so it's a quantum system in 2 dimension, in 2 space dimension.
Yeah, but I guess the goal would be to go, let's say, for the ground state, energy and wave function, not so much for dynamics.
Okay. So this is not reachable with the present tensor network approach. I mean,
from what I understand,
PEPS,
it's
called
but
PEPS.
I'm sure some people in this room know better, but I understand it's very tricky to get it right using those methods. But I guess the other speakers in this school know better than me how that goes. Yeah, I think I think Leuchli is the champion in simulating this classically, and I think he could do like a patch of 40 sites out of a 2D grid, and I think that's not big enough to have a solid conclusion on the nature of the ground state. Yeah, going beyond 40 classically is a very difficult thing.
Other questions? In the quantum chemistry problem, let's say the molecule of hydrogen molecule. So, do you learn something on the ground state if you look in the spin basis? But it is something.
So the question is about what you learn about the ground state for the hydrogen molecule problem. Yeah, so I guess, you know, when my optimization procedure has stabilized, I'm looking at a trial wave function that has everything in there, right? So both space and spin degrees of freedom.
The reaction is larger on the state 0011, so it's kind of.
So sorry, the interaction or?
No, I was wondering whether you could maybe understand something more in the spin basis about the ground state of the hydrogen molecule instead of looking in the fermionic basis.
Well, I guess, you know, you start with, let's say, an honest representation of both spin and position in the fermion basis, and then you simply translate to qubit language, and there you finish the analysis, so to say. And so I guess what comes out is a spin singlet state with a certain spatial layout, and that's the optimal state.
Okay, so other questions in the chat?
Yeah, so I'll add, you know, the number 5 part of my notes and problems. So please try the problems. They really help, I think. And I'm still here this afternoon in a discussion session, so I can give, for example, some hints if you need that to get going. And you know, after I'm gone, please don't hesitate to send me an email about these things, and I'll help you along.
Okay, so then let's thank Kareljan for his lectures and see you this afternoon. Okay, thank you.